Alright, in this unit we're going to talk about electrochemistry. Electrochemistry is the study of the interchange of chemical and electrical energy. Two processes that involve oxidation-reduction reactions are the generation of electric current from a spontaneous chemical reaction and the use of a current to produce chemical change. So to review, oxidation-reduction, remember, is a transfer of electrons from the reducing agent to the oxidizing agent. Right? So oxidation, remember, is a loss of electrons, and reduction is a gain of electrons. Okay, if you require a refresher on how to balance redox reactions, you may want to look at section 4.1 in your textbook. So galvanic cells are devices in which chemical energy is converted to electrical energy, and this is basically a battery. Right? So the oxidizing and reducing agents have to be physically separated so the energy of the reaction can be used. So we have the cathode, which is where reduction occurs, and the anode, which is where oxidation occurs. One way to be helpful to remember that is that cathode and reduction both start with consonants, and anode and oxidation both start with vowels. Okay? The salt bridge is a porous disk which allows the exchange of the ions to keep it electrically neutral while the solutions are separated. So basically you have a flow of electrons that go through a wire. So basically a cell looks kind of like this, and you have some electrodes. You have your solutions, you have some electrodes, and the electrodes are connected to a wire, which is then hooked up to a voltmeter to measure that voltage. And then the salt bridge connects the two solutions, and you have the flow of ions here, and you have a flow of electrons here. Okay, and so you have to keep the charges equal. So if the electrons are flowing this way, that means through the salt bridge, positive ions have to be flowing this direction to counteract the electrons. So electrons, remember, are negatives. If they're flowing towards the cathode, then the positive ions have to flow into the cathode. And then vice versa, since negative charges are leaving the anode, you need negative charges to flow through the salt bridge to here. Okay, in one of the other videos that I've posted, there's an animation of this that will be helpful to watch. Alright, so a redox review. So we want to identify the species in each of the following equations that would receive electrons from the cathode and which would lose electrons out of the anode. So in other words, what is the anode, what is the cathode? And there is an arrow missing here. Okay, so our first step is to break down the equation into two half reactions. So we have our magnesium going to magnesium plus 2. And remember, we have to be electrically neutral, which means we need 2 electrons over here. And then we have 2 hydrogen ions going to H2 gas. And again, we have to be electrically neutral, so this is going to also need 2 electrons. Of course, in this case, our electrons are equal, and so that's good. So then we have to decide which of these is reducing and which one is oxidizing. Remember, an oxidation is a loss of electrons, right? If it's losing electrons, then electrons are a product, right? So that means the magnesium is oxidizing, and therefore is our anode. Okay, and then the hydrogen ion is reducing, and therefore is our cathode. Okay. Now we can measure how much potential there is. So that's called our cell potential. How much electricity is being formed. All right, so the oxidizing agent pulls electrons through a wire from the reducing agent to the other compartment. The electrons flow from the anode again to the cathode. And a good way to remember this is A to C, alphabetical order. Right? The pull of the electrons is called the EMF, or electromotive force. And that's the force pulling the electrons towards, right? Or the force moving the electrons. Electromotive, moving electrons. Right? So the unit we measure cell potential in is called a volt. A volt is defined as 1 joule per coulomb. This distinction will become more important in our later section. The potentiometer is powered from an external source in opposition to the cell potential, and that's how we can measure that potential. The voltage is adjusted until no current flows in the cell circuit, so the cell potential is equal in magnitude and opposite in sign to the voltage of the potentiometer. Okay, so this is how they determined what the cell potentials are for different half reactions. So they had to have a way to relate those values to each other. So they came up with the idea of using a standard electrode, and they chose to use hydrogen as the standard. And so the standard to which all the other half reactions are compared to is our hydrogen. And again, we're missing an arrow here. And so they arbitrarily set the cell potential of hydrogen to be 0 at 298 Kelvin, 1 atmosphere, and a concentration of 1 molar. So these are what we consider our standard conditions. Okay? So when they did this, they created a list of potentials. And this list is found in your textbook on page 843. You do not have to memorize this list. You will always be given the information that you need to make these calculations we're going to discuss. Okay, but that's how they were determined, all experimentally and all based on hydrogen. So, in order to solve for E, or the cell potential, E is called the cell potential. Okay. So galvanic cells require that E be greater than 0, which indicates that it's spontaneous. So a galvanic cell is spontaneous. Okay. One of the reduction potentials will have to be reversed in every calculation. Since our chart is set up as reduction potentials, remember we have to have something to reduce and something to oxidize. Therefore, something has to be reversed so that it oxidizes. So to determine which one to reverse, we want the sum of the oxidation and reduction half reactions to be greater than 0. We want to make sure that E is positive. Okay, E has to be positive. So when we reverse a reaction, the E for that reaction gets the opposite sign. Okay. So when you multiply a reaction by a coefficient, as we were doing with enthalpy and entropy and Gibbs free energy, we multiplied the value of H, S, and G for each of those by the number of moles. We do not do this for E. Okay? E is not changed when we multiply our half reaction. Alright, so let's look at an example problem. So this example problem can also be found on page 844 of your textbook. Again, I'm missing an arrow here. Alright, so we want to determine the half reactions. Alright, so we have iron plus 3 going to iron plus 2. That's one of our half reactions. And again, to be electrically neutral, the iron plus 3 has to gain an electron to become the iron plus 2. We find that the cell potential is 0.77 volts. And again, that came from that chart in your textbook. And then the other half reaction is our copper plus 2 and 2 electrons going to copper. So if we look at this reaction up here, we see iron plus 3 going to iron plus 2. That matches what that is doing. So that is reducing. But here we see copper going from 0 to plus 2, which is opposite of this, which means we must reverse the second reaction. And so when we do that, we get copper solid going to copper plus 2 and 2 electrons, and then the E value becomes negative 0.34 volts. Okay? Reaction 1 has to be multiplied by 2. Why does it have to be multiplied by 2? Well, we have to have the same number of electrons. Remember that from redox reactions we did a long time ago. Right? So we have to multiply this by 2. And remember, we do nothing to the E value of E. So we're going to multiply by 2, so we get 2 iron plus 3. 2 electrons make 2 iron plus 2. And the value of E remains the same. It does not change. Okay? Now to get the overall cell reaction, we're going to sum these two halves. Again, my arrows are missing. All right, we're going to add them together. Since our electrons are on opposite sides of the arrow, they cancel out. So we get copper plus 2 iron plus 3 makes copper plus 2 and 2 iron plus 2. Excuse me. And to find the value of E cell, we do the same thing. We added the two halves together, so we add the values of E together. And so when we add those two together, we get 0.43 volts. Okay. And since our E cell is positive, it is spontaneous, which is what a galvanic cell always is and must be. Okay. Alright, so another example. So we want to consider this cell. Again, I'm missing my arrow. So first we want to determine the half reactions. So 1/2 is aluminum plus 3 and 3 electrons going to aluminum. Alright, so we find that on the chart. Alright, we'll find what E is in the chart. And then the other half would be from the chart magnesium plus 2 and 2 electrons and magnesium. So let's look up those values in our textbook in that chart. Give you a minute to do that. Alright, so we find in the textbook on the chart aluminum plus 3 right here, right, is a negative 1.66. And we find magnesium down below it is negative 2.37. Okay, again, the unit for this is volts. So we find those are two half reactions. Again, these are both reductions, but notice up here they did not both reduce, right? Your magnesium actually oxidized, so we have to reverse it. So we reverse the magnesium so it matches the equation above, and which means we change the sign, so now it's a positive 2.37 volts. Then we need to balance the half reactions, right? So we have 2 electrons for the magnesium, and we have 3 electrons for our aluminum. So we have aluminum plus 3 electrons. And we have our magnesium, which has 2 electrons. So to balance those out, right, we need to multiply this one by 2 and this one by 3. Again, that does not change the value of E in any way. So aluminum is still 1.66 volts, and the magnesium is positive 2.37 volts. Alright, so we get the overall balanced reaction by adding those two together. So we get 2 aluminum plus 3 magnesium, going to 2 aluminum and 3 magnesium plus 2, because our electrons will cancel out. And then we determine E cell by adding those two together. So our aluminum 1.66 and our magnesium, and we add those two together to get our final answer. And we get a positive 0.71 volts. Okay. All right. So another way we can describe a electrochemical cell is by what's called line notation. Okay. Anode compartments are always listed on the left side, and you'll see that in diagrams as well. And the cathode is always on the right side. Okay. Our phase differences are separated by a single line, meaning a single vertical line like so. And then they are separated by a double vertical line like so for a salt bridge.